At exactly 102 hours and 38 minutes into the Apollo 11 mission, the Lunar Module Eagle begins its final descent towards the Sea of Tranquility. With roughly 3 minutes left until touchdown, the ship is dropping fast. Suddenly, astronaut Buzz Aldrin reads out a program alarm, 12:02. Seconds later, it happens again. Then, a related alarm appears on the display, 12:01. Down in Mission Control, flight controllers have seconds to decide whether to abort the historic landing. Steve Bales and Jack Garman authorize the descent to continue. They say, go. But the 12:02 and 12:01 alarms indicate a condition the crew was never meant to see. The ship's guidance computer is struggling to process more data than its physical memory can hold. Surviving this data flood was the ultimate test of early software engineering, a set of recovery rules programmed into the ship's tiny, primitive computer long before it ever left the launch pad. To understand the pressure on the system, we must look at the Apollo guidance computer itself. Built in the early 1960s, its total power is microscopic by modern standards. The system's permanent memory consists of roughly 72 kilobytes of core rope memory. It was literally woven by hand. A wire threaded right through a magnetic ring created a binary 1. A wire routed around it made a 0. The active workspace, the erasable memory used for intermediate calculations, is even tighter. It has exactly 4 kilobytes of RAM to run the entire descent program. With a clock speed of only 1 megahertz, the computer lacks the brute force power to buffer tasks or allow work to pile up. It has no choice but to process every task in real time. Because the hardware was so incredibly scarce, the computer could not be designed to prevent an overload. Instead, it was engineered to survive one. The crisis during descent starts with a subtle mismatch in the hardware checklist. The rendezvous radar, a system used to track the command module, is left in the wrong switch position. That switch error causes the radar to send a continuous, unintended stream of data into the computer. The machine is suddenly flooded with a massive volume of extra job requests. This diagram shows the result. Every active job needs a tiny block of memory called a VAC area to run. There are only a handful of these in the 4 kilobyte RAM, and the useless radar requests are snatching them all up. Critical computations for the landing thrusters suddenly have nowhere to go. They need memory to run, but the system is full of radar noise. In most computers of that era, this total resource exhaustion would result in a fatal freeze, or silent data corruption as the system ground to a halt. Margaret Hamilton and her team at the MIT Instrumentation Laboratory designed the computer's executive software, a real-time operating system built for high-stakes environments. Instead of a rigid, sequential script, the executive uses asynchronous execution, breaking the ship's functionality down into small, independent units called jobs. Here is the key to the computer's survival: priority scheduling. Every job is assigned a numerical rank of importance. Essential guidance and thruster controls sit at the very top, while radar updates are placed near the bottom. The executive constantly scans this list. It has the absolute authority to preempt any running task if a higher priority job needs the processor. This architecture means the computer is never blindly processing tasks in the order they arrived. It is actively judging what matters most to the mission in real time. Back in the lunar module, the memory is full, but the executive recognizes that low-priority radar tasks are blocking the critical landing functions. The computer triggers a process called graceful degradation. It ruthlessly aborts the low-priority radar tasks, flushes their memory allocations, and drops the essential thruster controls into the newly freed slots. To inform the crew, the computer triggers a software restart for its non-essential systems and displays the 12:02 and 12:01 alarm codes. These alarms are status reports, visible signals from a computer that is successfully shedding non-essential work to protect the landing trajectory. Mission Control authorized the go call in seconds because they had been trained on this recovery design. They recognized the alarms as a sign the computer was working exactly as Hamilton's team intended. Neil Armstrong is able to focus on taking manual control to avoid a boulder field, a maneuver made possible because the essential software never stopped flying the ship. The Eagle lands safely on the lunar surface with roughly 25 seconds of fuel remaining. The successful touchdown of the Eagle proved that a resilient system isn't one that avoids failure, but one engineered to know exactly what to abandon when things go wrong.